Good morning, dear students. So far we have discussed yesterday D block elements. Today, let us move on to the F block elements. F block elements are an inner transition element. Inner transition element or rare earth element. All those three are same. Okay. So F block element or inner transition element or a rare earth element, all are same. Why they are called as a different name? F block elements. F block elements mean the differentiating electron, the lost electron or differentiating electron which enters into the F orbital. You know very well, already we have discussed in a periodic classification on the SPD block elements. Again I am repeating you. If a last electron enters into the S orbital, then it is called the S block. If the differentiating or last electron enters into the P orbital, then it is called a P block elements. When the differentiating or last electron enters into the D orbital, then it is called a D block element. When a differentiating electron enters into the F orbital, that is called a F block element. So here in F block elements, all those elements, the electrons, the differentiating electrons enters into the F orbital. That's why they are called as a F block element. Then inner transition element. You know very well, D block elements are called a transition element. But F block elements are called as a inner transition element. Why? Because it is inside of the transition series. You know the outline of the periodic table. It will be like this. S block, P block, D block. Okay. Here, the location of F block elements are here. Okay. So inside the transition series, the transition metal, D block elements are transition metal, they are located inside the inner part of the transition element. That's why they are called as a inner transition element. Okay, inner transition element. Then the availability in earth is very low. So they are called as a rare earth elements. So they are called as a rare earth elements. Now let us move on. What are the F block elements? After lanthanum to lutetium. So lanthanum is a D block element. Cerium to lutetium, here 14 elements. Then actinium to thorium to lawrencium, 14 elements. Actinium is a D block element. Okay. These 14, cerium to lutetium and thorium to lawrencium. These 14 elements are called the F block elements. Here, this is 4F. Here, actinium is 5F series. 4F series, this is called a 5F series. Why? Because the last electron or differentiating electron enters into the 4F orbital in lanthanides. So they are called as a lanthanoids. Lanthanoids nowadays, and earlier they are called as a lanthanides. Likewise, the 5F series, that is called as a actinides, nowadays actinides. Okay. Why sir, lanthanum is a D block element? Why you are saying lanthanides? This is after lanthanum. Here, after lanthanum, 14 elements starts now. So they are called as a lanthanides. All those 14 elements. Cerium to lutetium. Likewise, actinium is a D block element. After that actinium, 14 elements have a similar property. All the 14 elements, the last electron or differentiating electron enters into the F orbital. So they are called actinides. Okay. Now the scientists have confusion or a lot of problem is there. If they insert 14, already they fixed for transition element 4 transition series are there, 4 are having 10 elements. If you add a till more 14, the main sketch will be collapsed. Main sketch will be collapsed. That's why they have given allotted a separate sheet, a separate bottom of the periodic table. They have allotted bottom of the periodic table. They have allotted and locate the position for lanthanide and actinides. So they are totally called a F-block element. This is 4F series. This is 5F series. 4F series, 5F series. 4F series called as a lanthanoid. Lanthanoid or lanthanoids nowadays. 5F series called a actinoids. Okay. Then the position of the periodic table is like this. Here in the periodic table, if you give a place already 10 for each series in the D-block element, if you add till more 14, there will be a lot of confusion. That's why the scientists give a place at the bottom of the periodic table. So location of the periodic table, F-block elements in the periodic table, bottom of the periodic table is separated. That to 2 series they have divided. One is lanthanides, another one is actinides. The lanthanides are otherwise called as a 4F series. Actinides are otherwise called as a 5F series. This is the position and location of the lanthanides in a periodic table. Today let us see about the about the electronic configuration and atomic rating about the lanthanide. Tomorrow we can see the actinide. Electronic configuration of lanthanides. See, lanthanides the electrons are entering in the anti-penultimate cell. It is nth level. This one n minus 1th level. This is n minus 2. If it is a nth level, valency level, it is further inside n minus 1, then n minus 2. So, general electronic configuration can be given to the lanthanides n minus 2 F-block elements n minus 2 F 1 to 14. Then n minus 1 D 0 to 1 NS2. This is a general electronic configuration of F-block elements. So what is the N? N is a valence cell. If you take N equal to 6, you know very well F starts with a 4 only. N equal to 6. So if I am writing 6S2 for example. So what is the N minus 1? 5. N minus 1? 5. So 5D 0 to 1. Okay. Then N minus 2. That is 4. Yeah. So 4F 1 to 4. This may be an electronic configuration. Outer electronic configuration of lanthanides. It will be like this. Okay. This is called a valency level. This is called a penultimate cell. This is anti-penultimate cell. N minus 2. Okay. This may be a general electronic configuration. Now I am going to list out the general electronic configuration of all those 14 elements in the form of the table. So name of the element, let me list out lanthanum. Lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europolium, cadmium, terbium, dysprosium, helium, okay, erbium, erbium, thulium, ytterbium, at last lutetium. See, listen: lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, helium, erbium, thulium, ytterbium, lutetium. These are 15 elements. Okay. So let me write the symbol of this: lanthanum La, cerium Ce, praseodymium Pr, neodymium Nd, promethium Pm, samarium Sm, europium Eu, gadolinium Gd, terbium Tb, dysprosium Dy, helium DHO, erbium Er, thulium Tm, ytterbium Yb, and lutetium Lu. Okay, this is simple. Atomic number, you know very well: lanthanum 57. Starting from 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71. So these are atomic number of this. Then electron configuration. This is very, very important. If you memorize, it is very difficult. If you know how to fill it electrons, then it will be very easy to you to recall and reproduce. You know very well that is xenon 54. Okay. So all the electron configuration will be written as xenon 54, 4f, 1 to 14, 5d, 0 to 1, whereas 6s2. This is the general electronic configuration for a lanthanides. Now we are going to fill for each. Okay. Lanthanum. Lanthanum is a D-block element. There is no entry of the F orbital. So even though you are writing xenon, okay, xenon, 4f, 5d, 6s. You put like this first. Then you using the general electron configuration, and based on the atomic number you have to fill. Okay, S2, S always completely filled for all. Already xenon take a 54 electrons. 54 plus 2, 56. One more at D, so 0. So this is electronic configuration of lanthanum. If we go for cerium, 58 xenon, 4f, 5d, 6s2, 54, 56, 57, 58. Okay, one more. So that's why here there is no F electron, F orbital electron, but in cerium the last electron enters into the F orbital. That's why these 14s are called the F block elements. Likewise, before that you have to know that there is no F2 and F8. There is no F2. F2 and F8 electrons are not found. You remember. So here, the praseodymium, xenon, 4f, 3, 5d0, 6s2. Okay. For neodymium, xenon, 4f, 4, 5d0. Check whether class check whether it is equal. 54, 58, 60. Okay. Like that you have to cross check it in between. Promethium, xenon, 4F5, 5D0, 4S2, sorry 6S2. Now you check 54, 6, 61, and xenon, what is it? Samarium, 4F, 6, 5D0, 6S2. Europium, xenon, 4F7, 5D0, 6S2. Then gadolinium, xenon, 4F7 again, 5D1, 6S2. In order to stability, 4F8 you should not write. For the stability purpose, you are writing 4F7. This is off field. Then terbium, xenon, 4F9, not 8, because F2 and F8 is not known. 5D0, 6S2. You check it. For terbium 65, we are saying 65, 54, 54, 56, 65. Okay. Then dysprosium, dysprosium, xenon, 4F10, 5D0, 6S2. And xenon, 4F11, 5D0, 6S2. Xenon, 4F12, 5D0, 6S2. Xenon, 4F13, 5D0, 6S2. Then xenon, 4F14, 5D0, 6S2. For lutetium, xenon, 4F14, again not 15, only 14 electrons can accommodate in the F orbital, 3D, 5D1, 6S2. These are the electronic configuration of lanthanoid series. Okay. So what is, before you getting into the electronic configuration, you should know the general electronic configuration of lanthanoids. Here xenon, 4F1 to 14, 5D0 to 1, 6S2. If you know very well this, then you, based upon the atomic number, you can fill it up. See, always if you find difficult to memorize, just see, simplest way is there. You write general electronic configuration first, you fill it up, like always xenon, 4F5D6 is, this is series, filled. You write 15 times this. Okay, there is no change. Only number we have to alter. Based on the atomic number, you are going to fill from the S orbital. S orbital should be filled first. Then D. This is because of D block. D is going for D. Then D and F. Like this, you simply fill. The exceptional cases here. This one, gadolinium, because off filled. If you need to put F8, but there is no F8 at all. So this is in order to stability. Off filled F orbital, total number of electrons in the F orbital 14. If it is 7, it is more stable. In order the stability purpose, they are altering. So here you may get a off filled electron configuration with a D one electron. Likewise here cerium you may get a D electrons. Likewise at last lutetium, not lutetium, lutetium, you are getting that a D1. 1, 2, 3. In 3 cases only you will have a D electrons. 1, 1, 1. So in a lanthanoid series, what are the, except lanthanum is a D block already, that is we did not mention. Here cerium, gadolinium and lutetium. These 3 are having a D1. In addition to lanthanum we need to mention, lanthanum is a D block already. So in F block, those elements are having the D electrons, cerium, gadolinium and lutetium, unknown electrons are there. Then completely filled the lanthanum, F0, 4F0, no F electron at all. Gadolinium and the europium, we can say europium also 4F7 off filled. electronic configuration. F orbital is awfully filled there. Then lutetium and yttrium, they are having F14. So if they ask which are the gadolinium, they will mention only gadolinium, off filled, completely off filled. Then lutetium they will mention, and the empty F orbital in a lanthanum. These are the things we need to recall in the electronic configuration. Once again, based on the general electronic configuration, you may go with the like this. Okay. Then let us move on to the oxidation state. Dealing with the oxidation state of lanthanide. General electronic configuration, oxidation state +3 for all the 14 have a +3 oxidation state. In addition to that, +2 and +4 oxidation states are available. Okay. So the question may be asked, what is the common oxidation state? Common oxidation state is +3. Minimum oxidation state, lowest oxidation state shown by the F-block element, lanthanides are +2. Maximum oxidation state shown by +4. This may be asked the question. Common oxidation state, minimum oxidation state, maximum oxidation state. Okay. So who are they expecting the +2 oxidation? Other than all the 14, from cerium to lutetium, all the 14 will expect +3. That's why they are called a common oxidation state. Special oxidation state +2. Those who expecting neodymium, samarium, europium, thulium and yttrium. Okay, +4 oxidation state, cerium, praseodymium, neodymium, terbium and dysprosium. These are expecting the, in addition to that, so these two +2 and +3, here +3 and +4. So totally for neodymium you can have a +2, +3, +4. All those three oxidation states are expected. Okay. Then move on to the atomic radii. Let's start. Atomic radii. Atomic radii is regular decreases. You may find a very regular decreases in atomic radii. We move on the lanthanum to lutetium. So atomic radii decreases to 10 picometer. Ionic radii is found to be 20 picometer decreases for every atomic number increases. This is called this process. The steady decreases of ionic radii of lanthanide elements are called lanthanoid contraction. Lanthanoid contraction or lanthanide contraction. What is contraction? It is contracting towards. That is called lanthanide contraction. This is a 2-mark question we will ask. Define lanthanide contraction. The steady decreases of lanthanum 3+ ion, generally they will say Ln3+ lanthanum ions. Okay. The steady decreases of Ln3+ ion as atomic number increases, that is called the lanthanide contraction. So why the lanthanide contraction arises? What is the cause for the lanthanide contraction? So let me explain the causes for the lanthanide contraction is nothing but a poor shielding of 4f orbital. This is the first ever reason. Poor shielding. 4f orbitals are poorly shielded. So it can be explained like this. If you take a 4f orbital here, you find the nucleus here. This is assume that this is 4f orbital. Okay. Generally, 4f orbitals are poorly sealed because S is there, P, D, F is there, F is lost, so poorly sealed. Okay, towards the nucleus. The path is not there. The sealing is very poor. Poor sealing effect of 4f orbital only causes the lanthanide contraction. Now let me explain here. Cerium, if you consider cerium, starting from cerium 58 proton will be there. So here 58 electron will be there. So they are getting into this. Okay, the nuclear charge, as atomic number increases, the level 4f level, the distance between the nucleus and 4f level is not increases, but nuclear charges increases. Okay, so till 71 proton will be there, the distance kept constant, remaining same. So here inside the nucleus, inward pull will be maximum. So if the 4f orbitals will be, we are assuming to be here, but every atomic number increases, effective nuclear charge increases. Already it's poorly sealed, no? So they are getting into the inside. So our expecting size, if you like this, but it is not so, it is slightly decreases. So it is contract towards the nucleus. That is called lanthanide contraction. This is causes for the lanthanide contraction. Then what is the consequences of lanthanide contraction? The lanthanide contraction, it causes decreases in basic character. Basic character will be decreased, first of all. Then ionic character also will be decreasing. Ionic character decreases. Then the opposite, covalent character increases. Covalent character increases. Act as a reducing property. Reducing property also decreases. Then similarity. Due to the lanthanide contraction, similarity between the 4D and 5D series, there is a zirconium and osmium almost have a similar size. Same size. That is because of lanthanide contraction. And finally, all are having very close to each other, so separation is very difficult. Separation of elements is difficult. Separation of elements will be difficult. The basic character, ionic character, basic character decreases, ionic character increases, covalent character, basic character decreases, ionic character also decreases. Why basic character decreases? Ln, the distance between the metal and hydroxide ions decreases, means the bond between the Ln OH is also decreases. So they are tightly packed. In order to remove the OH is very difficult. Basic character is due to the removal of OH. It's very difficult. That's why as we move from lanthanum to lutetium, basic character decreases. Size decreases, automatically ionic character decreases, covalent character increases, basic character decreases. These all are in one point. Okay. Then basic character, then a reducing property. Already we have, there is a reducing tendency, reducing property also decreases. Basic character decreases, automatically reducing. For example, the question may be asked, lanthanum hydroxide, compare the basic character of lanthanum hydroxide and lutetium hydroxide. This is a very common question to be asked. Lanthanum hydroxide and lutetium hydroxide. Which is the more basic? Or compare the basic nature of the lanthanum and lutetium hydroxide. Due to the, what is the reason? Lanthanide contraction. Lanthanide contraction. Lanthanum hydroxide will be more basic than that of the lutetium hydroxide. Because lanthanum to lutetium basic character decreases. So lanthanum hydroxide, due to the lanthanide contraction, lanthanum hydroxide more basic than that of the lutetium hydroxide. Okay. Then because of lanthanoid reaction, almost the radius are very close to each other. Zirconium and hafnium, it is belongs to 4D and 5D series. Due to the lanthanoid contraction, the size is very similar to each other. Okay, then separation is difficult. All of having very small size, the separation of these elements are very difficult. These are the consequences of lanthanoid contraction. So the leftover points we need to discuss in lanthanoid. Promethium is a radioactive, man-made element, and radioactive. Okay, radioactive means specifically if you see in the periodic table, they will give. The question may be asked, which is a synthetic or man-made material element in a lanthanoids, promethium. Then uses are not given in your book. Just I am reciting for your knowledge. It may be asked in a neat question. It is extracted from monocyte sand. Okay, lanthanides and actinides both are extracted from the monocyte sand. This is not given in your book. Then the uses part. Uses are very important for lanthanides. Let me recite just you recall that. Lanthanides, the alloys of lanthanides are found in many uses in cigarette lighters, bullet traces. Likewise, there are many uses for alloys of lanthanides. Then very important, they are very strong reducing agent. The reducing property is utilized. Like aluminothermic process, there is a lanthanidothermic process. Aluminothermic process is nothing but iron oxide is reduced to iron by using aluminium. That is called aluminothermic process. Likewise, the lanthanides also used in the reducing process. So they are called as a lanthanidothermic process. Lanthanidothermic process is nothing but by using lanthanide elements for the reduction purpose. Then mismetal, it is very important metal. It is used to prepare a stainless corrosion resistant metal. Stainless steel and corrosion resistance purpose, the mismetal is found use. These are the uses of lanthanides. These points are not given in your book. Once again, I am telling what we have seen today. F-block element. F-block element is nothing but the last or differentiating electron enters into the F orbital. That is a n-2 F level. They are called as inner. Why they are called as inner transition element? Then there are two series. One is lanthanides, another one is actinides. Lanthanides, that is a last electron enters into the 4f orbital. Actinides is nothing but a last electron enters into the 5f orbital. Then let us move on to the electronic configuration. Electronic configuration, we have seen the tabulation, how to write the electronic configuration, what are the list of the all the 14 elements we have seen. Then we have gone for the radii, atomic and ionic radii. Atomic and ionic radii gradually decreases from lanthanum to lutetium. Okay, this is why. What is the causes for the lanthanide? This is called lanthanide contraction. Then what is the causes of lanthanide contraction? We have seen nothing but a single word we can explain that is due to the pore swelling of 4f orbital. That is called lanthanide contraction. Then what are the consequences of lanthanide contraction? Lanthanide contraction, first and ever consequence is basic character decreases. The ionic character also will be decreasing. Then automatically covalent character increases. Covalent character increases mean ionic character will be decreases automatically, basic character also. There is why? Because the basic character decreases, no? The L and OH bond, it is decreases. Whenever L and OH bond decreases, because of the lanthanide contraction, the size is very small, the covalent nature increases, that's why basic characteristic decreases. The reducing tendency, these are good reducing agents. The reducing tendency also reduced or decreases because due to the lanthanide contraction. The hafnium and zirconium almost a similar size, that is due to the lanthanide contraction. And the separation of lanthanide element due to the lanthanide contraction, it is very difficult. These are the consequences of lanthanide contraction. Then uses, that's all. Tomorrow we will see the actinide. Thank you.